Welcome, everyone. Really great to have you all here. My name is Risa Wexler. I'm the director of the Kavli Institute for Particle Astrophysics and Cosmology. And I'm just thrilled that you all were able to join us for our public lecture today. We are not in person today, but we still have a very special guest who's visiting us here at Stanford. Our lecturer today is Dr. Emma Chapman. She's a faculty member and a Royal Society Fellow at the University of Nottingham. Her research is focused on a really exciting period of time, about 13 billion years ago, just shortly after the Big Bang, when the first stars lit up the universe. So this is a really exciting time in the universe that we are learning more about. Her work focuses on the radio astronomy experiments that are trying to detect this information directly by measuring hydrogen. Emma, in addition to being an accomplished researcher focusing on this area, is a brilliant communicator, and she released her first popular science book called First Light. Really nice book, and in the context of this book and her other outreach work, she's been the recipient of many commendations and prizes, including the Royal Society Athena Medal. She's a wonderful public commentator on astrophysics, as well as on many topics in our field, including on gender equity issues, which we heard about from her earlier today at Stanford. She's regularly speaking at public events and the media. So let me just welcome Emma. Emma, please, thank you so much for joining us. It's just so nice to have you here. And I'm really looking forward to hearing more. Thank you. Before I pass it off to Emma, I'm going to pass it off to Sinan Du, who's KIPAC's Outreach and Engagement Manager, to tell you a little bit more about how things are going to work today. So thank you, Sinan.
Well, thank you, Risa, and welcome, Emma, and everyone. Thanks again for joining us at another KIPAC lecture. It's great to see some of you who have been following us for a while, and we also welcome those who just joined for the first time. So aside from Emma and Risa, I would also like to introduce others who are also joining us today at the event. So we have Dan, who many of you have already known from the previous event. And we also have 3 moderators that you will be seeing later in the YouTube live chat. So they are all subject matter experts studying in fields that are closely related to today's topic. So now I will let them to introduce themselves. Tom?
Hello, everyone. My name is Tom, and I study cosmology, and I am a physics graduate student here at Stanford.
Thank you. Welcome. And next we have Charles.
Hi, everyone, and welcome to the talk. My name is Charles. I'm a research scientist here at Stanford. My area of expertise is the sun, and I work on NASA's Solar Dynamics Observatory.
Very cool. Last but not least, we have Nick.
Yeah, hey everyone, I'm Nick. I'm a 5th-year PhD student here at Stanford, and I study what's called the large-scale structure of the universe. So that is, how did we develop all of these beautiful galaxies that we see out in the sky when we look up with our telescopes, and how do they relate to the sort of very baby picture of the universe that Emma's going to be talking about today?
Wonderful. Well, thank you all for joining us. So the chat moderators, they will be moderating the YouTube live chat, as you can see on the right-hand side of this page. We welcome all kinds of questions in the chat and also encourage you to engage in discussions. The moderator will be answering most of the questions as they come in, and the remaining questions will be passed along to Emma to answer at the end of her presentation. Since we have a relatively large group here today, we kindly ask you to be respectful to each other and in the chat. So without further ado, take it away, Emma.
Hi everyone, it's really lovely to be here. I'm going to share my screen with you. It should hopefully go seamlessly, I have no doubt. Are we seeing everything? I'm going to count to 3, and if I hear nothing, Excellent. Okay, I'm traveling here from University of Nottingham in England. I've been out here for 2.5 weeks now, absolutely loving it. And it's really exciting for me to get to share with you a bit of my research in an outreach form. So what I study are the first stars to exist in our universe. And I can't actually remember what the abstract is that I submitted for this talk, but I know that it will be very much along the lines of saying, well, there's this mysterious era that we really need to fill in because we don't have any data on it. Well, the wonderful thing is that very nicely timed. I'm hoping that at least some of you will have picked up on the news last week that the Hubble Space Telescope managed to detect light from 12.9 billion years ago from a star that emitted this light 12.9 billion years ago. So this is an incredibly early light from an early era. So I couldn't help but, I wouldn't even say crowbar this in, actually. It could have been written for this talk, so I'm quite pleased. So this is the image that came out from Hubble. The larger image you see here, this is a Hubble Space Telescope image with every single piece of light on here pretty much being from a galaxy. The Hubble Space Telescope is absolutely fantastic at seeing galaxies. It's been doing it for 32 years now, faultlessly pretty much. And it's really, really good at giving us intricate details in galaxies nearby, such as this image here, which is so pretty. I actually have it on my dining room wall at home. Because I just can't get over the different colours and the different, well, I guess the diversity of the shapes. I love the one on the left that's just hiding there, that little spiral, just chilling out over that. I just love it. I think it's amazing. So Hubble's very good at doing things in excellent detail, but as we go further away, as Hubble looks further and further and further away, things get very murky indeed. This is the Hubble Ultra Deep Field, another very famous image that is next to the other image on my dining room wall, on massive 1 meter by 1 meter canvases, because you can really get lost in this kind of image. So these are looking at galaxies even up to, I forget now, but billions of years old. And again, you can see the diversity of the structures here. You can see the spirals, the ellipticals, the reds, the blues. But you can also see that things are getting a bit fuzzier in terms of the background galaxies. Now, this one looks a little bit more underwhelming when you see it, I guess. And it's because we are getting to the point now where we're just looking further and further away. So this larger image is like the ultra deep field one that I just shown you. And this image will take up a very small portion on the sky. So if we were looking up, it would take up, and this is me guessing actually just looking at the scales, but it would take up less than if you held a little finger up at the sky at an arm's length. It's going to be a very, very small amount of the sky. But what they found was in the magnified image here, they found this tiny red dot, which has been helpfully pointed out with an arrow. And this tiny red dot is what we believe to be the farthest star ever observed. And they've called it Arundel. And that is from the Lord of the Rings, Tolkien kind of universe, which I used to be a really big Tolkien fan, but apparently this was mentioned in the Silmarillion, which I never quite got into. So Arundel was a character who would carry around a jewel called the Morning Star. And that's what Arundel means. It means dawn or cosmic star or rising light. And the idea behind this is that we are seeing we are seeing a star towards the dawn of our universe. So what I'm going to do is I'm going to use this observation that's very exciting and very timely to just introduce you into the kind of research that I do. And we'll talk about this discovery a little bit as we go, and I'll explain to you why it's red, why it's well, everything about it. This is not an intuitive image, right? And this is kind of what I want you to take away immediately, is that we are now getting into the realms of astronomy, that when we are looking at things so far away, so old, that it's not easy for our minds to be able to understand what's going on. You should have lots of questions, is what I'm saying. I had lots of questions when I saw this image. Why do I care about Arundel, and where do I do the research that I do? Well, it's because that we can be pretty smug about how much we know in terms of the cosmological timeline. We've got lots of information about things that happened recently or very near us, so the Earth, Mars, Moon, galaxies near us. We've even got a pretty good hold on what happened right at the beginning, the Big Bang. We've had observations which has really secured that as a theory within cosmology, which I don't have time to go into today, so you're just going to have to take it as gospel. But we have all of these simulations going back and back and back and back, simulations, observations, it's not the Matrix, going back and back and back and back, filling up our knowledge, except we are missing a large chunk of our understanding of the universe, of the baby stages, the baby universe, if you will. And this is not to scale, but we are missing around the first 800 million years, first billion years of our cosmological timeline. Now, if we try and think about that in human terms, if you had a scrapbook of somebody's life, then you compare that to this cosmological timeline that we have, then you would be missing every page from the page where they were born to the page where they first go to school. So you are missing out a huge chunk of knowledge. We are missing a huge amount of data. And when you're missing that amount of data, you have to start to worry about the conclusions that you're making for the universe that we see around us today, for our understanding of the science. I guess it's really pushing the analogy here, but it's kind of like, trying to figure out why somebody does something in therapy as an adult without knowing any of their childhood. It's a bit suspect. So Arundel, and I did check the pronunciation of this because I really feel like it should be Arundel, but I'm going to go with what NASA released and say Arundel. What we see here is we've magnified it even more now. They're getting very fancy. What they did was they looked at 41 images. So this team of astronomers, they're from the US, and what they did was they decided, we want to have a look at the oldest galaxies to exist in our universe. How are we going to do this? Now, being able to gather light from extremely far away objects, far away means in a moment, but gathering light in order to see very old galaxies is extremely tricky. And you can't just fire up the Hubble Space Telescope, point it in a direction, and stumble across a 13 billion year old galaxy or star. So what they did instead was they took a magnifying lens to the problem, and they looked for areas of the sky that had been naturally magnified by a really cool phenomena that in our universe called gravitational lensing. I believe we've got someone that doesn't know a lot about this on the chat moderation, I'm thinking. So hopefully they'll be able to answer any questions that I'm not able to, because it's the kind of that I was saying this to somebody the other day. They're like, oh, I really don't understand gravitational lensing. I'm glad you're here. And I was like, well, I don't really understand. Nobody understands gravitational lensing, really. It's incredibly tricky. And that's why I love science, right? Is that all of this is incredibly tricky. And the whole point of it is you should have questions. And if anybody tells you they understand any of these things like the Big Bang or anything like that, I think, yeah, anyway, getting off on one now, but gravitational lensing at its heart is about the distortion of space-time. So the distortion of space by a gathering of mass so gigantic. So we're talking, well, this infographic shows a galaxy, but most often, and especially with Arundel, it is a huge cluster of galaxies. They are so massive that they distort space-time such that actually light itself from a background source is bent around the galaxy. And as it comes to us, it is magnified. And so not only do we get to see something that you would have thought was hidden because it's behind this massive group of galaxies, but you also get to see something much brighter, because just like a magnifying glass, it magnifies as well. Now, there's also a phenomenon where, because hopefully you can see here that the light from the background source is spreading out as it does, and it's bent around the galaxy in two different pathways, except that it's around the entire thing, so it's loads of different pathways. And so as we see it, we can actually sometimes see these sources extremely distorted. So here is an actual image from Hubble, and you can see in the center the gravitational lens. So the lensing, I think this is a galaxy or galaxy cluster, I'm not sure, but the lensing structure in the yellowy orange in the middle. And then you can also see this light blue line all around it, and that is a galaxy. It's a background galaxy. It has been lensed, that has been distorted and magnified and brightened, such that we are seeing something much further away than we normally would be able. So that's pretty nifty. And this is what they did. So they looked at the Hubble images and they said, right, where are the biggest 41 clusters that we know about? Let's see if they've magnified anything. So they had a look at these images, and they found one. They found this one. And what they found was, and it's so subtle that you can't even really see the central lens as well as the image I showed you. But what you can hopefully see is a very thin, very red, very long line, an arc, and that is a galaxy. So that is a galaxy. I was just about to say a galaxy far away. Dear God, the cliche. That is a galaxy far away that has that's light has come across. It's on its way, come across this big mass. Its light has been bent around it. It's been distorted, and so we are seeing a galaxy that is about 13 billion years old. Well, light from a galaxy that has been traveling 13 billion years. That in itself is not so exciting. I mean, it's super cool, right? But we have seen galaxies that far back, light from that time. What makes this really interesting is that it's not only the galaxy that has been lensed, but there is this one little point, and unfortunately my Zoom thing is right in the middle of where I'm trying to point. There we go. There's this little red dot here that when they ran all of the simulations to see what was going on, they worked out that this red dot could not be explained by anything really other than a single star. To a great confidence, they know this. So there are a couple of things, and we can talk about it in the chat afterwards if you want. There are a couple of things, maybe it could be, but overwhelmingly, this looks like one single star in a very big galaxy lined up with this lens so perfectly that it was magnified about 1,000 times to the point where this star appears as large as star clusters that were also magnified, but you couldn't see the individual stars in them at all. And the whole galaxy is itself that big red strip. You could see it compared to that galaxy. I think that's quite incredible. So we've been able to look at all of the different the light from this source, and we've been able to figure out that this star we think is about 50 times the mass of our sun. It's about, I think it's, oh goodness me, I've lost it now. It's 10,000 to 20,000 times brighter. and extremely hot. So what is important to bear in mind here is, you might have noticed me dancing very carefully about my wording, and that's because we are seeing old light, not an old star. What this is kind of akin to saying is, let's imagine that what was the thing I had in mind? Yes, okay, so let's imagine that we're interested in Tutankhamun, for example. If you were thinking about an old star, looking at that kind of thing, then you'd be looking at Tutankhamun's mummy. Okay, so you're looking at something very old, you're learning lots about that. What we're seeing is the equivalent of, we're seeing old light, and that's kind of the equivalent of seeing an actual photograph, so not an artist's impression, a photograph of Tutankhamun as a boy. So he doesn't exist anymore. He's very much dried. But we can still learn a lot about this image from them at a much, much younger time. And so when we see this light, we are seeing an image of a time long, 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 long ago. And actually, Arundel, for reasons that I'll get onto a little bit later, is almost certainly long dead. And if we were around long enough, if we were taking observations for long enough, then surely we would see it, we would see it supernova. Okay. But this doesn't mean that it's not interesting. And so there's old light and old stars. And both of these are ways of filling in that era of the first stars that I have done my research on so far. So let's just talk about old light for a moment. And I mentioned that this star that has been observed by Hubble is what we think is the farthest star to have ever been observed. And I'm kind of using the terms farthest away, earliest, looking back in time, all of these kind of things interchangeably. And that is because light isn't infinitely fast. And that means that when you do look further away, you are looking back in time. And this is what makes astronomy so cool. And it's one of the reasons that I ended up doing, actually, is when I learned about this. So let's imagine that we're waving to our friend on the moon. The light from the source that we're using, so let's flash a torch, let's make it easier. Let's flash a torch at our friend on the moon. The light from that torch will take about 1.5 seconds to get there, about 1.5 seconds to get back. It's only been 2.5 seconds. Everybody's happy. Now let's imagine that we are doing the same thing to a friend on Mars. Now it's going to take 4 minutes for them to see us. It's going to take 4 minutes for us to see them replying, by which time it's been 8 minutes, and we're pretty sure that they've actually just walked off and completely ignored us. So things start to break down a little bit compared to what we're used to. Now let's move it right back. And let's go to the one of our nearest galaxies, Andromeda. So we are signaling our friend in Andromeda, and it takes 2.5 million years for the light to get there. And it takes that time to get back, by which case we are very much dead and don't really care that they've ignored us at all, because it's been 5 million years. What this means is that by the time we get that signal back, we are seeing our friend as they were 2.5 million years ago, even though they're long gone. And what really brings this home when I think about it is that in this lovely situation, if there is some kind of extraterrestrial intelligence happening to look at light from Earth right now, they are not seeing us, whatever we're doing as humans right now, and being human, basically. What they're seeing is 2.5 million years ago, which is when the earliest ancestry of humans existed, and that's the kind of Earth that they are seeing right now. So all we have to do as astronomers is look at light that has traveled so far that it's taken 13 billion years for that light to get to us. So we are seeing the universe, we're seeing that object as it was 13 billion years ago. And that's what's happened with this first star. And that what my entire research area has been around. So it's very easy to think that we're just kind of turning on a Hubble Space Telescope and looking at a pretty star and going, oh, look, we found one. It's not that easy at all. It really is looking back in time, deciding where to look. And yeah, okay, I think I've just made that point. Now, this image, we will quite possibly not see the like of it again. And that's why this was so exciting, because it completely blew the previous record out of the water. So the previous record was a star called Icarus, and the light from that had been traveling to us for 9 billion years, compared to this one, which was about 12.9 billion years. And I don't know, I guess maybe you'd think, well, okay, who really cares? There's always going to be a high record. We'll just keep going. Actually, the chances of this single star lining up with this lens so perfectly is really quite small. And of course, we cannot choose where these gravitational lenses are. We have to just go with the universe and see if we have been lucky. So it takes a huge amount of skill, a huge amount of theoretical work to understand what we're doing, technology to actually be able to carry this experiment out. But also we're limited, unfortunately, by a little bit of luck. So we need to look at different ways to find things. And one of them is by looking at different kinds of light. So how do we know that Arundel is so old? And the answer is that it's very red. So you might think, well, hang on, look, you've got lots of dots on this image. Some of them are a bit whiter. How do you know that's not a star from this time? Light is really very useful. It's very useful in daily life, but it's also useful to look back in time, and it's really useful for determining age as well, because it has some pretty nifty properties. And that is that it comes in a whole spectrum, a whole load of flavors. So and all of these you'll be familiar with in daily life. You've got radio, you've got infrared, you've got optical, you've got UV, and you've got X-ray, as well as some other types in between, microwave, for example. We're used to the optical. Of course, this is what our eyes have evolved to see. But the point is that there's all of these different things that we could actually use here. And we have just used, mostly in astronomy, that little bit in the middle, that optical one, which is a tiny portion of the entire spectrum. Now, as what you might notice below is actually what I've done here is I've put what is called the wavelength of light. So we can think of light as a wave, and we can think just as if you're kicking your feet in the water. If you kick your feet slowly, then you have very long distances between the crests of your waves. We call this long wavelength, and that's like your radio light. And then if you kick your feet really, really fast, then you've got very short distance between the crests of those waves. You've used lots of energy to create that, and you've got a much higher energy, shorter wavelength light like X-ray. Now, as the light from these stars travels towards us, it is fighting against the expansion of a universe. It's fighting a heck of a lot, and it's had to travel for 13 billion years. It loses energy along the way, and so it travels down this spectrum, or rather its properties move down this spectrum. So if it's emitting X-ray, it will lose energy all the way to radio, given enough time, given enough distance. And so with Arundel, we're pretty sure it started out fairly blue. In the optical, it was emitting blue optical light, and actually it's taken 13 billion years for that to travel towards us, and it's what we call redshifted. And so the actual observed image that we see is this red blurry dot. And so by seeing the fact that it is so red, by seeing lots of other pieces of the galaxy that it lies within, then we can say, yeah, okay, we're pretty sure that this is a very, very early light. So it looks like we've actually got one of our first pieces of information in this lost billion years, this lost era of the first stars. But there's a heck of a lot more to fill in. And it's another thing is that it's important to note is that it's an early star. It's not one of the first stars. And because the first stars were a completely different species. Arundel's a very old star, don't get me wrong, like it's one of the earliest stars there possibly, there could have been, but it's not one of the very first ones. And we know that because we have studied its light and we know what it's made of. And we know that it has got what we call metals inside them. And by metals, I mean anything above hydrogen and helium, because stars, what happens is you have a huge gravitational force pushing together the very simple atoms and molecules right at the center. So in the very early universe, all you've got is hydrogen and helium. And when you have these first stars, they fuse together this fuel. This energetic reaction gives out heat and light and everything we love about the sun these days. And it creates larger molecules. So hydrogen, helium, lithium, beryllium, boron, carbon, etc. The oxygen we breathe, the carbon we're made of. But in the very early universe, it's very pristine, it's very clean. And it's only when these first stars die and supernova and pollute the surrounding universe with all of these metals that we can actually start to form the next generation of stars. And so by looking at the metal content of this star, we know that it's not completely metal free. It's not one of the very first ones, but it is tantalizingly close. So what can we do now? We can't really wait around, just hope that we find another lens that has perfectly aligned. And indeed, what we do again is we use light again. And what I have devoted my career to is not using optical light, but using radio light. So right down at the low energy area of the spectrum. So astronomy is very used to using lots of different kinds of light. This is a galaxy seen only in optical light. This is a galaxy seen with radio light as well in the orange. You can see that not only is the galaxy much larger than we thought it was, there's all this hidden gas that we can suddenly see, but we can also diagnose things about our universe that we didn't know. So for example, when you look at what could cause these massive radio jets, actually the only thing really that we know of is the fact that there's a black hole at the center of them causing this emission. And it's, I mean, the images now that are coming out, it's an old one, but this is the Whirlpool galaxy here, optical in the middle, and then in the orange you can see the radio. And you can just see these radio arms, it's astonishing. And we use all of this different kind of light together in order to learn lots more about our universe. So my favorite thing to do is to go and see radio telescopes and have my dorky picture taken in front of them. I make no apologies. The middle one is me last week. The Allen Telescope Array, about 4 hours north of San Francisco. The one on the left is me last week in the Space Sciences Laboratory of Berkeley. So that's actually tracking a space satellite at the point. And on the one on the right is me at Jodrell Bank in Manchester, my local. And so they look very, very different to Hubble Space Telescope. They're on the ground to start with. And you can get less, or should I say, you get more underwhelming if you're used to things like the Hubble, and you can get very tiny antennas and dishes, that the kind of things you would have just stuck on your house, to be honest. But we can put them all together and we can listen to the universe, and we can start to see energy, light that has lost so much energy that it has been redshifted right down into the radio. And that's what we're trying to do with these experiments now. So we are trying to do what Hubble has done with Arundel, really, and look for this early light, but we're trying to push back even further right back into about 200 million years after the Big Bang. So really filling in that entire era. And one of the ones that we're building at the minute is called the Square Kilometre Array. This is in the Western Australian desert, and you can see the antennas here. We call them Christmas trees, and we decorate them accordingly because we do normally have one in every office of the people that are building them, because there's been so many models. But we're going to have 130,000 of these across the Western Australian desert. We're going to hook them all up, and it's going to work as a gigantic telescope in order to look back right to the start of the Big Bang and hopefully fill in a lot more than just this very early star. So to finish off, I want to just talk to you about the other option that we spoke about, which was not seeing old light, but actually thinking about looking at an old star. So this isn't looking at those photographs of Tutankhamun as a boy. This is actually by, really digging in the ground, entering the pyramids, dusting stuff off, and trying to find evidence from long, long, long ago that we can use to inform our knowledge. And the reason I keep going into Egypt is because I never actually wanted to be an astrophysicist. I wanted to be an Egyptologist. It's what I did everything to do. I did all of my options. I spent my Wednesday afternoons packaging 5,000-year-old shoes in one of the most famous Egyptology museums in the world, until a fateful day when I picked up a book at the local library, because I'd read all of the ones in Egypt, and this one was about how you could look back in time if you were an astronomer. And I thought, my goodness, I wanted to look back 5,000 years. You're telling me I could look back 13 billion? Yes, please. And so I changed all of my options. I changed my application for university from Egyptology and ancient history and all of this, and changed my options to do maths and further maths and physics, and eventually to do physics and astronomy at university. So yeah, one book really affected me. Now, when we're looking for old stars, what we need to be careful of is, well, how do we even start? Because one thing I told you is that Arundel is, well, it will be dead. So if it is 50 times the mass of our sun, we know that by now it will have burnt through its fuel, it will have fused all its fuel, so that it will have gone into a supernova and it would have been obliterated. No more light for us. The first stars, the very, very first stars, they're even larger. So we think that they were even up to 100 times the mass of our sun. There's some simulations that suggest you could get the odd one that's 1,000 times the mass of our sun and a progenitor of very, very large supermassive black holes. And because we know that if the more massive star there is, the faster it runs through its fuel. So a star like Arundel would live, a few tens of millions of years. One of the very first stars would have lived about 1 million years. And this is all compared to our sun, which we hope will survive up to 9 million years. It will, don't worry, of which we're about 4.5 billion years through. So there really is a big difference here. So if we want to see old stars, then they have to have actually survived up until this day. So we need to find stars that were actually very unusual for the very first era. And those are stars that aren't 100 times the solar mass, because they're just normal back then. What we need is the tiddlers. We need stars that are only around 0.8, 80% the mass of our sun. They will have eaten their fuel slowly enough that they will last the full 13 billion years. And they could still be hanging around today in the Milky Way. The problem is that they aren't going to be easy to find, even if we know that they are completely metal free, even if we can look at the light and say, actually, this tells us what's in there, there's not many metals. And that's because they've been hanging around the universe for 13 billion years. And even though they started off very, very pristine in a lovely, lovely clean universe, the universe has not stayed clean. All the other stars have died and polluted it with metals, and so they have accreted it onto them. They've become camouflaged. And it is the job of stellar archaeologists, and I'm not making that term up, it is a field that you can get into. And it's the job of a stellar archaeologist to look at all the different stars they can and try and figure out, is that camouflage or is that actually just a much younger star? And there's a heck of a lot of stars. So just to end, I want to just leave you with the thought that this is an extremely challenging problem, and stumbling across Arundel in the way we did obviously took a huge amount of skill to know where to look, but it also it took a lot of time as well. And what you don't hear about, for example, how Tutankhamun was discovered, so I'm not sure if you know the story, but Howard Carter was digging in the desert, and supposedly he comes across this buried tomb, and it ends up being one of the most pristine Egyptological, if not archaeological, finds of all time. But what you never hear is that Howard Carter didn't just stumble across it. Howard Carter gridded out this whole patch of desert in Egypt and searched it for 5 years. And for 5 years, he found nothing. And actually, his patron, Lord Carnarvon, said, "That's it. You've had enough of my money. You found not a sausage. You're not doing it anymore. You quit." Howard Carter begged for one more dig. And quite particularly, what did he find? The greatest discovery of all time in this era. So science is hard. It requires a lot of skill, a lot of technology, a lot of enthusiasm and grit to keep going, and a tiny little bit of luck. But with all of those things together, we can use the old light, we can use the old stars, we can look back in time, and we can do some incredible science and hopefully fill in this era, this billion years that we are missing. Thank you ever so much for listening to me. And yeah, I hope that I can convince you to think about those stars when you look upwards and how far back in time that you are seeing them.
Okay, thank you so much, Emma. That was really fantastic. I learned a lot from that. And I, in particular, loved what you said at the end about how it takes both planning and also kind of grit and enthusiasm to make new discoveries. So that's really fantastic. Okay, so we have lots of questions from the audience, and if you have not yet asked the question that you want to ask, there's still a chance. So let me start with a question. This is a question from the audience from Anirban Das, who asked, why don't we see the host galaxy of Arundel in the same image that we saw that star, the thing that was doing the lensing? Why didn't we see that?
Okay, so we did see the galaxy. It's just that it was so distorted that it had been, it just looked like a very thin red line. I can't remember what they called it now. I think they called it the sunrise arc, something like that. And it's so stretched out that you can barely see it. And it's like if you imagine holding a really thick magnifying glass over something that you're trying to see, you can't just plonk it over and look. You actually have to kind of adjust it and move it and see how it gets into the focus. This isn't a perfect analogy, but what I'm saying is that yes, you can see the galaxy, but it is that one star that aligned just perfectly with that glass that actually, that's what pops out at you.
Yeah, that's great. Okay, awesome. There's a great question from Quinde Tarja, who asked, basically, how do we know the age of the stars that we're seeing? How do we know, how old they were when they were formed? How old the universe was when they formed? How do we know those ages?
That's a question that I can't really answer in detail without an infographic that I have. But we have studied so many stars, and we have understood what we call stellar evolution, how a star evolves over time. We're used to seeing our sun not really changing that much. It will have tantrums and throw out particles at us, but it doesn't really change that much. But when we look at all of the stars around us, what we're actually getting to see is a snapshot snapshot of all of the different lifetime stages. So it's like taking a snapshot of a busy supermarket. You'll see babies and senior citizens and pregnant people and adults, and using all of that, all of these images we have, we can piece together this jigsaw puzzle of how stars evolve over time. And then when we look at a new star, we can say, what does that fit best with? And sometimes, yeah, we won't quite know whether it's a young red one, so an old red one, or a young blue one, or but it's by looking at a heck of a lot.
Yeah, great. This is an interesting question. So we know that a lot of the stars that are much more nearby have planets. What about the first generation of stars? Should those be expected to have planets? And would the planets be different, or would they, mostly be, helium and hydrogen gas giants? Or what kind of planets? Do you know anything about that?
Yeah, and I'm afraid it's a fairly underwhelming answer in that no, they wouldn't have had planets, and that is because they were born and died so fast that there just wasn't chance for a planet to form. So if you think of a human lifetime again, compared to a human lifetime, let's say that's the sun, the first stars would have lived the equivalent of 3 days. It's a very small amount of time, and it's actually so short that in that early universe, you hadn't even formed galaxies at that point. These stars tended to hang around in much smaller groups. And it's only when this very first pristine generation ran through its fuel, died, polluted the universe, and then the second generation could form. It's only then that you have enough time to assemble a galaxy without it just blowing itself to smithereens. So unfortunately, no, planets would have come along a lot later.
Right. So you need two things, right? You need the stars to be old enough and have long enough lifetimes, which you don't get from the first ones. And then you also need them to have more metallicity and dust around them to be able to form the planets, right? Yeah, great. So I'm wondering if you could say a little bit more about like the next decade of radio astronomy and what you're most excited about.
Sure. Well, the last decade, we've been taking data to really dig into this era, and we've had a couple of what we think might have been the first detections of this era. The next decade is really about running with that, about making sure that we've seen what we think we've seen by repeating it all over the world, but also just building the most. I mean, the square kilometre array, the SKA, that's the one I'm involved in helping to build. When you think about putting 130,000 of these antennas on the ground, the moment that you switch that on, in optical, you get this launch, right? You get fancy things and clean rooms. And I mean, I burst into tears when JWST went up at what was the equivalent of midday when I was in London. With radio, you don't really get that because you kind of just switch it on. But the science that's going to come out of the square kilometre array, we're going to be able to actually make a movie of the gas around the first stars over the entire billion years of that lost era. So we're going to be able to watch our universe evolve over the first billion years. And so this really is equivalent to not just having an image of Tutankhamun as a boy, but a home movie of his first 5 years. That's what we're going to be doing in the next decade.
That's great. We have a question from Brian Day, which is related to my question. Can you talk briefly about the plans to build radio telescopes on the far side of the moon to prevent some, to provide some shielding?
I can talk for hours about this one. Yeah, so this is kind of what we'll be planning for in the decade after, the next decade. But because we're astronomers, we have to play the long game. And so we are starting to look at this now. The problem with making any kind of observation on Earth is, especially in the radio, is that it's very, very noisy. So we have to deal with microwaves, with planes going overhead, with mobile phones. So that's why we're in the desert with all of these things. if we can go to the far side of the moon, then suddenly all of that mess is blocked out so that we can get a really clear signal. The problem, of course, is the money it takes to get there, but there's a heck of a lot of will, and quite a few billionaires now that we're hoping might think this is a cool little fun thing to do. One of the ideas that's favourite to talk about it is landing 50 lunar rovers on the moon, each with an antenna on its back, and then you just the idea that you can look at the moon and on the far side there's going to be 50 of these things just doing a little dance, moving around until it's in the configuration that you want to make the kind of gigantic radio telescope that you want. Very briefly, the only caveat here is that while we treat the moon as this very quiet, silent place, because everyone is going there now, it's actually getting a lot noisier very quickly. And so unfortunately, we're having to go with that as we evolve these plans as we go, and be a bit realistic about that.
Yeah, super interesting. Related to the lensing that you talked about, we have a question from Jennifer Hicks, who asks, how do we know that all the light we see hasn't been bent by space-time?
My God, that's just blown my mind. And this is why I love doing these things, because I get questions where it's like, I've never thought about that. What if all of the light is big? I don't have the answer to that. I know that all mass will distort space-time in some measure. Even me, I'm distorting space-time right now. It's just that I am so little in the grand scheme of things, is that it doesn't bend the light in any way that we can observe with the instruments we have. So actually, yeah, all light is being lensed in this way. It's just that we can only notice when it's been bent and distorted so much that you see these gigantic arcs.
Yeah, absolutely. I think that's a great answer. And another way to say it is that most light is traveling through a universe that has some mass that has distorted it a little bit. You showed a really extreme example. Most light is only a tiny, 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 tiny bit that you can't see in this way. So that's great. Let's see. We have time for just a couple more questions. We have a nice question from Renee Hadnout, who's asking about old stars. How do we distinguish kind of the dust from the stars that have been polluted by metals? Classic question in astronomy.
Dust. I don't actually deal with dust a huge amount. So if somebody in the moderators panel has a better answer for that, but it will almost certainly come down to the ratios of the different elements in that. You know what, I always say to my students, admit when you don't know something. I'm going to admit I don't know this.
Yeah, so I'll give it a try. Actually, there's a sort of a known degeneracy that it's easy to confuse old stars with stars that have a lot of metallicity, and if you just look at the colors, it's actually quite hard to tell them apart. So getting more information like their spectrum can help that. Let's see. Well, maybe let me ask one more question about kind of what's coming next. We hear a lot about seeing more about first stars or first galaxies from JWST. Could you say something about how JWST is complementary to measurements that we can take in the radio?
Yeah, JWST has a huge role to play. It's mainly observing in the infrared. That's excellent for seeing stellar nurseries, for example. So you can see something very different with that. In terms of the era of the first stars, which is the era that obviously I know the most about in terms of this, it's going to be able to see galaxies much farther back than Hubble. So we're going to be able to see a much earlier universe in terms of that kind of complementary way. It's not going to be able to get right back to the era of the first stars and fill it in any comprehensive way. But there is one exciting possibility for my field, which is that what if one of these first stars they supernova in incredibly bright explosions, a very, very particular kind of supernova, which is extremely bright. If that happens to be behind a gravitational lens, completely coincidentally, then there is the chance that JWST might see that explosion. So whereas it will not see a first star just too far away, it could see a first death. It could see the death of the first star, which is an exciting possibility, very complementary. Again, you're adding all of these different diagnostic tools in all together. That's how we're doing science now. It's the era of, what is it, multi-messenger astronomy, right? You need all these different kind of messengers.
Yeah, I love that idea of seeing the death of one of the first stars. Coming back to what you told us about the planned search for Tutankhamun, JWST has a small field of view. So how likely is it, or is there a way for us to better plan to get lucky like that?
I think it is. The papers I have read on it have said it's possible, but not probable.
Yeah.
And so during, I can't remember now, but over years of JWST, you're looking at seeing a couple to a few, if you're lucky. So put it this way, we are not banking on this. If we get it as a lucky bonus, fab. But yeah, this is, I mean, I'm gonna blow my own trumpet here. Radio observations of the first stars is the best and the most guaranteed way of filling in this era, and that's why we've put so much money and so much effort into doing it, because it's pretty much the only way we're going to be able to learn about our baby universe.
Yeah, I think it's really, really exciting to think about what we're going to learn from SKA and other radio telescopes in the next decade or so. Well, okay, I think we are almost out of time. So let me just thank you again, Emma. I really enjoyed the talk and we had a fantastic audience. I want to thank everyone for their questions. I also want to let the audience know that, that we will be back in person for our next lecture. Emma is actually the first of a series of 3 fantastic female cosmologists we have who have recently written books, and I'm very, very excited about that. So Emma, I just really appreciate it. I'm gonna pass it off to Sinan before we end. So go ahead, Sinan.
Great. Thank you, Emma, for a fantastic talk. And I also saw that there was a lot of discussion and engagement in the live chat. So thank you all for tuning in. Before we end, as Risa said, we are actually going to be hosting the next public lecture, most likely to be hybrid on May 10th. So the speaker will be Chanda Prescott-Weinstein, and she will actually be talking about her newly released hard copy book, Journey into Dark Matter, Space-Time, and Dreams Deferred. So in the talk, she will actually be taking a holistic look at doing particle astrophysics and cosmology. So if you're interested, there are different ways to follow us that I'm just going to be giving a quick plug. So one way to follow us is actually directly typing in KIPAC, and then we have this public lecture series called Discover Our Universe. So basically /discover, and we post all our upcoming lectures here. And of course, if you're interested, you could also choose to sign up for our email list. This link will also be included to you in an email tomorrow. And we also have social media. How can we miss Twitter and Facebook? So Facebook, we are just the Kavli Institute for Particle Astrophysics and Cosmology. We not only post upcoming events, but there are also different interesting articles or blog posts that we do, news items if you want to follow us here. And likewise on Twitter, our Twitter handle is @KIPAC1, and we tweet all kinds of things. So if you want to follow us in any type of way, feel free to. And finally, we would also appreciate your feedback to our public lecture series and also specifically for Emma's presentation today. So for an email that I will send out tomorrow, you will actually be receiving a short feedback form. We would really, really appreciate your feedback on how we did today, whether you have other topic suggestions for future talks, and we would love to hear from you and improve as we go forward. So yes, any final thoughts, Risa?
No, that's great. Thank you so much. And thanks to the audience. Thanks to Emma. It was really fantastic to learn about this era of the universe.
Absolutely. And I also want to bring everyone back to the screen. Let's also give our chat moderators a round of applause. They did a fantastic job tonight. Yes, well, I hope that you all enjoyed this lecture and hope to see you very soon again, either in person or online in May.
Thank you, everyone.
Thank you. Bye.